Today's lesson is about alkenes and alkynes. Alkenes are the hydrocarbons with at least one double bond present, and alkynes are the hydrocarbons with a triple bond. So we'll begin with alkenes. You'll notice that the general formula, CnH2n, is slightly different than what we had for alkanes. And with the double bond, we lose two of the hydrogens. If we're looking at the formula C4H question mark, there are 4 carbons. When n equals 4, to find the number of hydrogens, 2 times n, 2 times 4. So we're expecting 8 hydrogens to be in an alkene with 4 carbons. And it would contain one double bond there. So, to go through the bulleted points, we've already said that alkenes contain at least one double bond, and the fact that they do makes them unsaturated. So we have ethane and ethene drawn here. You can see that ethane, the 2-carbon alkane, is saturated. Each carbon has 3 hydrogens around it. As soon as you introduce a double bond between the carbons, the hydrocarbon becomes unsaturated. So having 2 carbons on an end carbon is less than the 3 that would be the maximum if there had been a single bond there. And so unsaturated hydrocarbons contain double and or triple bonds. Moving on with the naming, you'll find that the naming is very similar to the steps that we've been following. The key is that when you find the parent chain, it must include the double bond. So the longest continuous carbon chain that includes the double bond is the parent chain. And when you're numbering, regardless of where the side groups are, give the double bond the lowest possible number. So we'll see the suffix of ene instead of ane, and you'll see I mentioned diene and triene. Well, we'll show you those when we get there. So I'm asking you to draw methane. So when you think about drawing methane, meth tells you 1 carbon in the parent chain, and when you see the ene, that tells you there's a double bond between carbons. So is it possible to even draw a 1-carbon alkene? No, it's not. So you need to have at least 2 carbons in order to put a double bond between those carbons. And so the smallest alkene is ethene. Eth meaning 2 carbons in the parent chain, and the ene meaning that there's a double bond between them. So 2 carbons with a double bond, and then we complete the octet by putting in the remaining hydrogens. And you'll see the formula here of C2H4 corresponds to our general formula of CnH2n. So let's move on to propene. Monkeys eat peeled. 3 carbons. ene for the suffix means there's a double bond. It means there's 1 double bond. If the suffix is diene, it means there's 2 double bonds. If the suffix is triene, it means there's 3 double bonds, and they will be numbered. However, when it's just ene, just ene, then there's only 1 double bond. So go ahead and draw propene. Now, it doesn't matter if you position the double bond between the carbon on the left and the middle carbon. No, it doesn't. If you had chosen to draw it between the carbon on the right and the middle carbon, then you would see that in numbering this, we would number from right to left for this structure, and we'd number from left to right here. Either way, that double bond is showing up between carbon 1 and 2. So these 2 structures are the same, so I'm only going to draw it once. So let's move on to butene now. So bute we know means 4 carbons. So I have 4 carbons drawn in the parent chain. 1, 2, 3, 4. And you'll see that I positioned the double bond between carbons 1 and 2. But someone else might have drawn the 4 carbons, 1, 2, 3, 4, and chosen to position the double bond between carbons 2 and 3. A third person may draw the 4 carbons and position the double bond on the far right. Then I would number from right to left, and that would mean that the double bond is coming after carbon 1, which is identical to the first structure. So this really isn't a third arrangement. So in shifting the double bond to a different spot, I have changed the structure. So it's not enough information to just say butene. And that's why in the steps earlier, I said when you get to 4 or more carbons, you have to number the location of the double bond. So in fact, this structure is not just butene, but but-1-ene. So this number 1 tells us the location of the suffix, and it comes right before the suffix. An older naming system, before the IUPAC rules were revised, would have called this 1-butene. And so you may see that in some textbooks or online references. But really this is the old way of doing it. The newer and current way is to number the functional group of the double bond with the number right in front of the ene. So what would you call this second structure? It's not just butene, and it's not but-1-ene. Hopefully you're thinking but-2-ene. So the double bond falls between carbons 2 and 3, and we always choose the number that is lower of those two in order to indicate the location of the double bond. Now, a point about drawing alkenes with line diagrams or skeletal formulas, we draw them with the zigzag. So it's not actually the same angle that we saw with the alkanes, but that subtlety really isn't picked up when you draw the skeletal formula. So the same zigzag is appropriate, and we go ahead and follow the same naming rules. So we will number the carbons from left to right or right to left, whichever direction is going to give the double bond the lowest possible number. So for this first example, and feel free to pause the video and work ahead of me, but we'll number this 1, 2, 3, 4, 5. So there are 5 carbons in the parent chain, and the double bond comes between carbons 2 and 3, and so we choose the lower of those numbers to indicate the location of the double bond. So try the next view. So we number again the parent chain, giving the double bond the lowest possible number, and so with 5 carbons in the parent chain, numbered from left to right, pent-1-ene. Now this next structure, the one right here, this was a tricky one. I purposely made the horizontal single bonded chain longer than the one with the double bond. So I was trying to emphasize the rule that the longest continuous carbon chain that includes the multiple bond is the parent chain. And so we'll put the double bond with the lowest possible number, which means it'll begin at carbon 1. And you can see that I found 5. If I had gone from the double bond to the left, I would have only had 4 carbons. So it's pent-1-ene. There's an ethyl group off of carbon 2, 2-ethyl pent-1-ene. Now for the next structure, you'll see that there are 2 double bonds, so that should trigger the di-ene. And just like when there are 2 prefixes, 2 side groups, you need to number each side group. When there are 2 double bonds, you need to number both double bonds. And so I'm going to number from left to right, 1, 2, 3, 4. That would put my double bonds after carbons 1 and 3, and it would put the side group on 2. Now if I had numbered from right to left, it would still put the double bonds after 1 and 3, which is the same then from both sides, but it would move the side group to carbon 3. And so since the double bonds are going to have numbers 1 and 3, no matter which way I number, then I will definitely go from left to right to give the side group a lower number. So monkeys eat peeled bananas, buta, 1, 3, di-ene. Now, it's a little bit tricky sometimes to remember to have this A here, and so the key is that if this letter here is a consonant, then you have that A there. So buta 1,3-diene. And don't forget that 2-methyl up front. Okay, any questions? Make sure you jot them down and I can answer them in class. Moving on to the next example. Give this one a try. Okay, so I have a chlorine side group at the far left and a double bond at the far right. So in terms of priority, the multiple bond, whether it's double or triple, will always have the lowest possible number if the side groups are just halogens or other hydrocarbon side groups like methyl, ethyl, etc. So I'm going to number this from right to left so that the double bond has the lowest possible number. In doing so, that makes the chlorine off of 6 and the double bond after carbon 1. And so the name is 6-chlorohex-1-ene. Cycloalkenes can be a little bit tricky. There's one key idea, and building on the idea that the double bond has to have the lowest possible number, in a cycloalkene, the double bond will always be between carbons 1 and 2. So if I number it as 1 and 2 here, then I move around the ring counterclockwise at this point, and I call this cyclohexene. Now your textbook is going to number that double bond, so they're going to write cyclohex-1-ene. I won't mark that wrong in this case because I think it happens too many times in your textbook for me to really expect that, but really, we don't need to number that double bond. When there's only one double bond in a ring, it's always between carbons 1 and 2. So move on and try the next diagrams, and then check in with the video. So similarly to cyclohexene, we have cyclopentene. I chose the top carbon of the double bond to be carbon 1, which meant that I numbered towards the double bond and clockwise this time, which gave me cyclopentene. Now, in trying the next structure, I know the carbons of the double bond need to be carbons 1 and 2. And if I start here and move down towards the methyl group, then I've ignored the double bond. And so that is not okay. If I'm going to start at the carbon that I've indicated as 1, then I must number counterclockwise. In doing so, that will put the methyl off of carbon 4. Well, I do have another option. What if we numbered the double bond carbon here as 1, this one is 2? That would put the methyl off of 3, which is lower than it was the other way around, and so in fact this is the preferred method. So looking at this numbering, pause the video and construct the name. Okay, and so we have 3-methyl cyclobutene. So the double bond was between carbons 1 and 2, and the methyl is off of carbon 3. Now the textbook would say 3-methyl cyclobute-1-ene, and I won't mark that wrong if you throw that 1 in there at the end. Okay, so move on and try the last two structures here. Okay, for the cyclopentene structure, we can see the 2 bromo side groups, and so we number to give the double bond the lowest possible number. In the ring, it's always between carbons 1 and 2. So I'll number, as you can see, clockwise from the bottom left, and that will put the double bond between 1 and 2 and the 2 bromine groups off of carbon 3. 3,3-dibromo-cyclopentene. And for the last structure, there are 2 double bonds, so we're setting up a diene, and in order to number that in such a way that the double bonds have the lowest possible number, you can see the numbering. So 1,3-diene. We see the methyl off of 2, and it is a cyclic structure, and so we have 2-methyl cyclohexa-1,3-diene. Okay, the final part of the lesson are the alkynes, and with the presence of the triple bond, we have lost 2 more hydrogens, and so the general formula CnH2n-2. Alkynes, as I say in the note here, will contain at least one triple bond, and that's most commonly what you're going to see. If there were two, it would be a diene or a triene, but really we'll commonly see the triple, just one triple bond. These are also unsaturated hydrocarbons. It's only the alkanes where the carbons contain the most number of hydrogens possible. And so alkanes are the only saturated hydrocarbons. We will explore shape in more detail in our second unit. However, when you have an opportunity to build the models of the alkynes, you'll see that there's a linear shape, and so we reflect that in the skeletal formulas or line diagrams. So try to remember then that alkynes, there's no zigzag when we draw those. The same naming rules apply as they did for alkenes, so whether you see a double or triple bond, make sure it's part of the longest continuous carbon chain. And again, it takes priority over halogen or alkyl hydrocarbon side groups. The suffix will be -ine, spelled Y-N-E. And so we start with a molecule known by its common name, acetylene. This would be used in blowtorches for welding. And we see it's a 2-carbon alkyne. And so we think monkeys eat. E stands for eth. And then we use the suffix YNE to show the presence of the triple bond. So pause the video and answer the next 2 questions and then check back in with me. Okay, so hopefully you have named these propyne, numbering from right to left, and pent-2-ine, numbering from right to left. We didn't have to number the triple bond in propyne because if there are 3 carbons and you put the triple between the left and middle carbon, then you'll just start numbering from the left, and that would put the triple between 1 and 2, exactly the same way it is in the structure that you were naming in the example. So again, it is when you have 4 or more carbons so just like with the alkenes, that's when you will need to number the triple bond. Okay, the last couple of examples here mix things up a bit. There's a double and triple bond present, so I just wanted to introduce you to these, which are a little more challenging. Seeing as we have both a double and a triple bond present, they're both need to be part of the parent chain. So number 1, both the double and triple bond need to be part of the parent chain. Secondly, you number to give them the lowest possible numbers. They're both going to be suffixes, and they're both going to need to be numbered. Any alkyl side groups are named as they normally are. So I'll take a moment now and pause the video and see if you can figure out the name. And I've just added in here just to note that for the ene suffix of ene, that I've dropped the e since another suffix is being written. So that's something to pay attention to. Okay, beside this, I've drawn the line structure for 2-methyl-hex-1 and 4-ine because I just wanted to show you what that would look like, since I mentioned earlier that the carbons of the triple bond will be linear in shape. And so you'll see that I have carbon 6 here and carbon 5, and I didn't zigzag because we're looking for linear or 180 degrees bond angle around carbon 5 and around carbon 4. So this shape will be much better understood when we study shape theory, molecular shape theory, in our second unit. So on the organic unit test, I will only expect you to draw the line diagrams correctly for alkenes and alkynes, but this linear idea in the alkynes, I'll reserve that for testing on the second unit once you've studied the shape theory and better understand it at that point. Okay, so just to finish numbering this, you can see carbons numbered from the right, 1, 2, 3, 4, 5, 6, And there's the methyl coming off of carbon 2. Okay, so that's the end of the video. I will see you tomorrow.